Hey guys, how you doing? This is going to be the beginning of the notes on momentum. So we're going to start off with a couple questions about what inertia is. So what is inertia? Inertia is going to be an object's resistance to being accelerated. And I'll share a post of these notes as a PDF to Google Classroom, and you'll get an actual version you can touch, a hard copy, when you come to class. What factors affect the object's inertia? There's only one thing that actually affects the inertia, and that is the object's mass. So this is going to determine how hard it is to accelerate something. Momentum is not the same as inertia because momentum is both the mass, the inertia part, and velocity. And this is going to be a lowercase p is equal to m times v. The units are kilograms, meters per second, or newtons times seconds. And we'll see newtons times seconds when we talk about impulse, which is change in momentum. If any of you guys ever used model rockets when you were a kid, you would have seen on the engines they actually say what impulse is provided in newton seconds or kilonewton seconds. Direction is going to be important for momentum because it's a vector. And so if you have components, you're going to have to break them into components and balance them, which hopefully you saw when we did the demonstrations. A 40-kilogram curling stone slides across a frictionless sheet with a velocity of 4 meters per second. What would our momentum be? So first we're going to start with our equation, which is little p is equal to m times v. And so this is going to be 40 kilograms times 4 meters per second, which is going to be 160 kilograms meters per second. So it's a product of both the mass and the velocity. A little bit more complicated problem. A lawn jar, 1 kilogram, is dropped from a window 15 meters above the ground. What is the velocity as it reaches the ground? And what is its momentum? We have two different ways to solve for this velocity. So we could do that energy is conserved. And so you would have potential energy at the top and kinetic energy at the bottom. Potential energy would be mgy. Kinetic energy would be 1/2 mv squared. I would cancel out the mass, multiply by 2, and square root. And we have 10 meters per second squared. And that's negative, and that's negative. And so it looks like I have the square root of 300, which would be 17.3 meters per second. Or we could say our initial velocity is 0. Our final velocity, we don't know. Our acceleration is -10. And our displacement is -15. And so if I look at my v squared equals v naught squared plus 2a x minus x naught, v is going to be equal to the square root of 2a x minus x naught, and then this would be the same as we had previously. So this is going to be 17.3 meters per second. Both of these are plus or minus because we square rooted, and I'm going to pick minus because the lawn chart would be going down if you dropped it. And then to get the momentum, we would just do the mass times the velocity. So this is 1 kilogram times negative 17.3 17.32 meters per second. So it's negative 17.3 kilograms meters per second is our momentum. So it's a vector, and since it has that and it has direction, we're going to have to break it into components. All right, so when we talked about the first two laws, we talked about them in terms of F net. And we talked about the first law, when forces are balanced, when F net equals 0, and that's when we're moving at a constant velocity or not moving at all. And we talked about the second law. If we're speeding up or slowing down, we used F net equals ma. If we're changing direction, we used F net equals mv squared over r. And I never talked about the third law. The third law comes in with collisions. It's when things are interacting with each other. And the third law tells us that for every force, there's an equal and opposite force. The reason that it seems like the forces aren't equal is because rarely are the masses the same. And we saw this a bunch in the demonstrations that if you haven't had class yet, we'll be doing the first day back. So if you think about a bug and a windshield, when you're driving down the street and you run into a bug, your windshield hits the bug exactly as hard as the bug hits the windshield. But because the mass of the bug is so much smaller, it's a way bigger deal to the bug than it is to the windshield. Some doctoral students did a paper on this, and they found out that the magic speed for bugs is 39 miles per hour. If you run into bugs below that, they bounce off. If you run into bugs above that speed, they actually splat. So that's the difference. Same thing with the nail and the hammer. The hammer hits the nail just as hard as the nail hits the hammer, but it's a much bigger deal to the nail because it's so much less massive. If you think about the head of the hammer, that's why it has a lot of mass to it, and it's a bigger deal, and it causes a bigger effect on the nail, or a face and a fist like this picture. So this fist is hitting the face just as hard as the face is hitting back on the fist. These are equal and opposite forces. We never see these on the same free body diagram because the free body diagram just shows the forces on one mass. And in this case, we have two different things. There's the force of the face on the fist and the force of the fist on the face, but those are equal and opposite. Another example is that you are being held down to the earth by your weight. The earth is also being pulled up by a force that's equal to that. That's a much bigger deal to you than it is to the earth. Or when I walk forward, I am pushing the ground backwards and the ground is pushing me forward. So me pushing the ground backwards is an equal force in magnitude to me pushing the earth backwards. But again, it's a bigger deal to me than the earth. Here's an example from your book. This person is karate chopping a desk for some reason. So they're hi-ying right there, and the force of their hand down on the desk would be this arrow, and the force of the desk on their hand would be that arrow. But these are equal and opposite. I didn't introduce them before because I didn't want to confuse you, because we always just talked about the one mass and the forces that are on that. You would never have a action-reaction pair in the same one. Here's yet another example from the textbook where the person is pushing on the wall and the wall is pushing back on the person. So it's always on different objects, and that's why they don't show up in the same F net. This is a convenient way to explain how rockets work, and even rockets in deep space when there's nothing to push against. The idea is that you could explain rockets that were pushing against the air outside of them, but really you're expelling fuel out the back with a certain force. That fuel is pushing back on the rocket with the same amount of force. So it does not require there to be an atmosphere. So rockets would work without an atmosphere. And here is another picture where you have the force of the ground on the person and the force of the person on the ground. And they're equal but opposite signs. So equal in magnitude, opposite in direction. And we saw this previously in two different parts where we had negatives that they were opposite directions. We talked about Hooke's law and when you talked about universal gravitation.